Okay, problem.
Thank you, Lester. So this is the fourth course out of 6, so it's time for the mid-course exam. Are you ready? Well, okay, let's do it together. I think you can be ready. Yeah.
You have to lock the door before saying this.
So in fact, I'd like to summarize the CFTs we've already discussed, starting with the simplest one, of course, the generalized minimal model. So the first thing is for which values of beta squared does this exist? So let me remind you that beta squared is notation for the central charge. So generalized minimal models exist for any complex beta squared, but it's not quite clear what happens for rational cases, so let's leave them out. And then in each CFT, I would like to indicate the spectrum of primary fields. So starting with the degenerate field, BRS, degenerate or just fully degenerate. Then we may have non-diagonal fields. And then we may have diagonal fields. So in generalized minimal models, do we have degenerate fields? Anyone? Yes, so that's even the definition of generalized minimal model. We want all possible degenerate fields, meaning all integer values of the Katz indices RS. So here I'm writing the possible values of the parameters. And then we have something else in the spectrum. Well, no. In here. Okay. Then we have Liouville theory, which we can get as a limit of generalized minimal models. Well, for C less than 1. If C is more general, well, we don't get it as a limit, but we assume it exists with the same spectrum. So, what is beta squared? So eventually, it's any complex central charge. Are there diagonal fields in the spectrum? Anyone? Are there degenerate fields? I mean, oh, no. Non-diagonal fields. Well, we are still in diagonal CFTs, so we are just taking diagonal field with any ideal momentum. But then we should extend Liouville theory. So that's denoted with a tilde by adding more fields so long it's consistent. If we do that, we can add, in fact, any degenerate field here. So we get an extended CFT which also includes generalized minimal models. And then we can take any complex momentum. Okay, so we have also seen A-series minimal models. And now the beta squared becomes rational and positive. I mean, I've given an argument that if it's not positive, then essentially you don't have a minimal model, meaning a rational CFT, a CFT with finitely many primary fields. So what are these finitely many primary fields? Well, basically the indices RS must belong to the Katz table, so they must be integer, of course, but also in some rectangle, so that you have finitely many. And then from these A-series minimal models, we could take limit. By taking limits, we could recover generalized minimal models. We could recover Liouville theory, but if we took a very fine-tuned limit, we could also get Runkel-Watt type CFTs. Again, at rational beta squared, where the spectrum is just as in Liouville theory, but the CFT was different. In particular, the fusion roots were non-trivial in these Runkel-Watt type CFTs. So these were the diagonal CFTs, and then we looked at a couple of non-diagonal cases, starting with D-series minimal models. So here again, Q over P. I mean, beta squared is rational, but now P was even. Then the spectrum was made of diagonal degenerate fields here, except that the first index was odd. So they are still in the cat stable, but not the whole cat stable, basically half of it. And then we added non-diagonal fields. So as a remainder, this non-diagonal field, VRS, they have left and right dimensions of the type delta RS, delta R minus S. So in this case, the values of R and S following 2z times z plus 1/2, but in some rectangle minus q over 2 times minus q over 2 q over 2. So these fields, well, they look like they have non-integer indices, so they don't look like degenerate fields, but nevertheless they are degenerate by some identity of conformal dimensions that exists at rational central charge. And then we could take limits of D-series minimal models to more generic value of the central charge. And this gave us what I call generalized D-series minimal models. So here, the central charge could be anything so long the real part of beta squared is positive. So that was a generic consistency condition for any CFT with degenerate fields and non-diagonal fields. And then, well, in this limit, in this non-rational limit, basically all these degenerate fields become non-degenerate. So instead of having here a spectrum of degenerate fields, we find a continuous spectrum there. As for the non-diagonal fields, what happens is just that this rectangle here, it gets infinite, so it disappears, and we just get this lattice 2z times z plus 1/2. Okay, so that's just the CFTs we obtained by assuming the existence of two independent degenerate fields. So the VD21 and VD12. And now we'll discuss loop models, which are obtained by assuming we have only one degenerate field, VD12.
Sorry, it's probably a stupid question, but you said you assume that you have two degenerate fields, and then for Liouville, you say there are no degenerate fields in the theory.
Yeah, so that was the distinction between spectrum and extended spectrum.
Okay.
So having degenerate fields in the spectrum is not the same as having the existence of degenerate fields. So I say they exist if you can add them consistently. And in all these cases, you can consistently add all degenerate fields you want.
But theory is not like Liouville versus Liouville. So this is this level. What's the difference between that and like a tensor product of Liouville and the two sectors? Are they constrained to interact with each other?
Yeah, so indeed, what is Liouville tilde? So Liouville tilde, if you want, is a set of correlation functions where you can have any of these fields. So for example, you could consider a 4-point function with some fields, some diagonal fields with any complex momentum. And then you could have some degenerate fields as well. So R3, X3, R4, X4. Or let's even take a 5-point function. So VP5. And you compute them by, well, decomposing to conformal blocks using the OPs we have written, basically.
I think the question is, does it factorize? Factorizing the correlation function for Liouville and
No, it doesn't factorize.
Is there something special about Liouville that allows you to have these fields? That's cool. Check any other CFT you have? Like when can you not a consistent way?
Yeah, that's a good question. But the point is the existence of degenerate fields will give us strong constraints. In particular, it will determine, as we'll see later today, it will determine the 3-point function. So if you assume, then you have a very restricted set of possibilities, in fact.
And then there'll be some recipe to posteriori determine whether it was consistent or not.
Yes, well, if you know anything about your CFT, well, you can look at the correlation functions and see if they obey the constraints you have from degenerate fields. But we'll see these constraints later today, in fact.
For instance, you take RWT, does not.
This one?
Yeah.
Yeah, no, it does.
So you could add,
Yeah, you can consistently add degenerate fields.
then you could add another line.
Yeah, well, I'm not extending systematically all that I could extend, indeed.
Are these unextendable?
No, well, my statement that they all have this field means that at least all of them can be extended with all degenerate fields to begin with. On the other hand, this CFT, well, it's not analytic basically in the momentum, so probably you can't have complex momentum. Because as we saw, we have fusion rules which involve basically step functions in the momentum, so it would not be natural to take complex momentum.
So how do you replace the let's say the column gas or the syncopative theory in this? There is a theory which is consistent, which is based on column gas integrals. Yeah. Do you say that it coincides with the generalized minimal model or?
Okay, so for the others, I mean, the Coulomb-Gas integral is the idea originally, I think, due to Dotseco and Fatev, that you write this series of perturbations of free bosons, and this helps you to compute correlation functions. So I view it rather as a technique for computing correlation functions. It's just that I will not use this technique at all. But when it works, it gives results which are the same as the results I will talk about.
So you will see that it coincides with, for example, the generalized minimal model.
Right. I think if you compute correlation functions in generalized minimal models, you can either compute them using these Coulomb-Gas integrals or compute them using the bootstrap, as I will do. The results are the same.
To summarize this, you're asking, what is the axiom, given a CFT, what is the axiom that to determine whether you are or are not allowed to add the degenerate field?
Well, you can assume you have it, and then you follow the consequences. So, for example, if we have this V12 plus VRX plus some non-diagonal fields, you remember it implied that R, the first index, was half integral, basically. So that's a strong constraint. I mean, if you violate it, then you can't have V12 in your CFT. And it also implied that R was conserved modulo integrals, and you might easily violate that in some CFT.
A general axiom, or just a patchwork of statements?
Well, let's say I tried to give all the statements that are known, but I mean these are really fundamental hypotheses, like adding this degenerate field.
Would you say you follow the consequences? I guess I want to know, given what pops out of that, when do you get to say whether that was okay or not?
Yeah,
like
right.
earlier you alluded to this elasticity property in the meta, which seems like a thing. I'm trying to keep track of it.
Yeah. Well, this is the axiomatic approach. You continue until you meet a contradiction.
But with what? That's what I'm asking. Yeah, with what set of axioms? Maybe there's not a clean answer, but that's what I'm trying to get. Is there, with what set of axioms?
Well, the axioms were the existence of the OPE, We had assumptions of the structure of representations also, that L0 was bounded from below. I mean, these axioms which I basically gave as we went, right? Indeed, my axioms were a bit, if you want, tuned to get the known CFTs and maybe some more. But then each time we have an axiom, we can think what happens if we change or relax the axiom. I mean, I'm not sure that these axioms are really fixed. Or, I mean, in rational CFT, you have maybe a more consistent and well-known mathematical framework. But here we are typically non-rational CFTs, so I'm not sure the theory is as well understood. Okay. So let's now eject one of our degenerate fields and keep only this one and see what we can get. And what we can get is called loop models. So they are called loop models due to their original construction from statistical models of loops and lattices, which I will talk a bit later in the course, but not today. Today I want to argue for loop models purely on general CFT grounds. So basically from this axiom that we have this degenerate field and not the other. So the first question is how does it constrain the possible spectrum? So let's write what I will call loop tilde. So the largest possible spectrum I can get provided this degenerate field exists. Well, not just the spectrum, I want to know for which values of beta squared it exists. Well, that's easy. We had this constraint that root beta squared is positive, and that's all we have as a general constraint. So this was equivalent to real part of C less than 30. That was, if you remember, from the convergence of operator product expansion. So in loop models, what can we have as degenerate fields? Well, we want V12, and then if we fuse V12 with itself, we get more. For example, V12, V12, well, you get V11 plus V13. And if you fuse again with V12, you get more degenerate fields, but always with the first index being 1. So the set of degenerate field is basically 1 times n star. So the set of possible indices. Then what about non-diagonal fields? So we had this OPE V12 VRS equals VRS plus or minus 1. And then in this OPE, we assume that all fields have half-integer spins. So the conformal spin is just SRS, is the left dimension minus the right dimension. For one of these fields here, it's R times S, or maybe minus R times S. And it has to be integer. It has to be integer for each one of these fields, in fact. And this is what implies this constraint that R is half integer. So let's have R half integer. Well, I can even take it positive integer. And then S, well, S just has to make sure that the spin is half integer. So 1 over 2R times an integer. And then for diagonal fields, well, I also know the OPE of V12 with a diagonal field. It was sum Vp plus minus 1 over 2 beta. But it doesn't really constrain the spectrum. So a priori, I have to allow all possible complex momentums.
Showing that R is a half integer. Remind us where it comes from.
Yeah, so it comes from assuming this spin here, and also these spins are half integer. Because then if the spin is R times S, and if you compute the difference between this spin, so let's say RS plus 1 minus RS, the difference between this spin and this spin, well, you just get R. And then these two spins are half integers, so they are different zones, so it's half integer. Okay, so we get, let's say, extended spectrum, which is pretty much all we can have in this type of loop models. Now there are subtleties here. So the first subtlety is, why do I take R to be strictly positive? So first we have well, the reflection relation, which is VR minus R minus S equals VRS. So this one allows me already to have R positive. Then why not R equals 0? Well, the point is that a field of the type V0S is in fact the same as a diagonal field. I mean, the definition of diagonal field was not just that the spin was 0, which is the case here, but it was also something about fusion rules. So if your field is diagonal and you fuse it with V12, you should still get fields with 0 spin. But this is the case here. If you look at V12 times V0S, you get also fields of the type V0 something, so their spin stays 0. So this is a diagonal field, and in fact, we can compute its momentum. We can rewrite it as a field with momentum 1/2 beta minus 1s. And equivalently, a field Vp can be rewritten as a non-diagonal field V0 2 beta p. So this identification will make our life easier, because basically we will work with non-diagonal fields, but the results will include also diagonal fields. Okay, so the other subtlety about the spectrum is that, I mean, I started in the course by defining a spectrum as basically the space of states. And here I'm just giving you a list of primary fields, which is not quite the same. Well, of course, typically if you have a primary field, you deduce the corresponding Verma module, the corresponding representation of the Virasoro algebra, and it gives you the spectrum, but that's not always the case. So if you have null vectors, you can build several different representations from the same primary field, and I would have to specify which representations I'm considering. And this problem arises in particular if for non-diagonal fields here, if R and S are both integers, non-zero integers. In this case, I must have some null vector either on the left or on the right. So, and if I have these null vectors, I have to say which representation I'm considering. In fact, I don't have much choice, because I can always get VRS here by taking VR0 and fusing with the degenerate field V12. Well, maybe I fuse several times, but in any case, I get VRS from VR0. VR0 itself is non-degenerate. It doesn't have any null vector, so it lives in a Verma module. And this OPE basically can be used to determine the structure of the representation for VRS. And then it has to be some logarithmic representation, but it's completely determined. Okay, so that's all I want to say about the spectrum of the. So then, what else can we say without getting into much detail? So first, we know how it depends. Well, we know the values of beta squared. We also know that the model is not invariant on the beta goes to 1 over beta, because when the indices R and S are symmetrically. So the true parameter for the model is beta squared. Not the central charge. So for each value of the central charge, we have two models, in fact, which are related by this beta goes to 1 over beta. Okay. And then we see that we allow any diagonal field with any complex momentum. And this raises the question of whether should we consider it as a continuous spectrum, and do we include basically Liouville theory in these models? And the answer is no. So, and I will I will take it as an axiom. So I'm assuming that any OPE spectrum is discrete, meaning no integral in the OPE, unlike in Liouville theory. Well, there are other formulations of the same idea. Well, I wouldn't say they are mathematically equivalent because I can't prove it. But, well, one other way of saying it is that Liouville theory is just not included in this loop models. Or another way of saying it is that correlation functions are meromorphic in beta for any, well, on the whole range of values. On this whole,
Which means that the full spectrum in principle contains all of these CP for complex P, but only in discrete set of them appears in any given OPE.
exactly. So in any given OPE, we get, in fact, finitely many diagonal fields. So then let me think why it means that correlation functions are meromorphic. Well, basically, it's because we saw in Liouville theory that they are not meromorphic because of this continuous spectrum. So when we took an OPE, like VP1, VP2 equals integral VP plus descendants. I mean, the descendants came with some OPE coefficients, which we know have poles. And due to the poles of these OPE coefficients, we had this problem that we could not continue analytically the correlation functions from the line T less than 1 to more general complexity. So that was not possible because of all these poles. And so if we had a continuous spectrum, we would have the same problem as the non-analyticity on this line. But then, well, I'm assuming the spectrum is discrete, so we expect, in fact, that everything is meromorphic on the whole range of values.
Really, having poles doesn't harm for being meromorphic. So what do you mean by there are poles in the OPE coefficients, so it's not meromorphic?
No, I mean, it's a bit worse than that. The poles are dense, in fact, on this line to begin with.
So poles dense means they are not.
Right, if you want.
That's fine, I understand.
I mean, we view them as poles because if you take an OPE, you have I mean, each term in the OPE has only one pole, basically. And then, moreover, it's not just that the poles themselves, it's how they behave as a function of beta. So as a function of beta, we saw that these poles, which were dense in a line, as soon as beta becomes complex, they all jump out of the line. And that's what made this non-analytic.
So what you assume is not that a given correlation function is meromorphic in beta. You must assume that some kinds of sets of correlation functions are meromorphic. Just one. It's not just one by one.
No, here this assumption means each correlation function is meromorphic in beta. Okay. Apart from that, we have some constraints on the OPEs already in this loop model. So we know OPEs of the degenerate field, which I already wrote there. We know these constraints that R is conserved modulo integer, which was a consequence of the monodromies of this degenerate field, basically, in any correlation function. And well, that's pretty much everything we know about OP. So we can't say much more for the moment. So for this sketch of loop models, let me finish by sketching examples of these loop models. So specific CFTs which have a modular invariant partition function and which have been studied previously. So the first one is the ON model. So let me argue for the spectrum of the ON model based on general grounds. So first I want all the spins to be integer, not just half integer. What can I have here if the spin is integer? Well, I can, it's 1/2 n star, but now 1 over RZ. So the product now is an integer. And then, however, this restricts the degenerate fields which I can have. Because if I had V12, I would do an OP like that, and the spin could become half integer. So if I want it to stay integer, I have to restrict a bit my set of degenerate fields. I need the second index to be, in fact, odd. And that's it. So that's, well, my attempt at giving a natural argument for the spectrum of the ON model. Okay, then let's define the UN model. So the UN model is pretty much the same idea, but now I'm insisting on keeping all possible degenerate fields here. And so it is now the VRs which I have to constrain if I want to keep the spin, the spin integer. I have now to take R to be in itself integer. And finally, there is the Potts model. So the Potts model, well, I can't really give an argument based on purely CFT or about its spectrum because it's just a small modification of the UN model, but which is not particularly natural from our point of view. So the modification is now that the VRS, the first index has to be more than 1. So it starts at 2 now. But then I'm replacing this non-diagonal fields which have been ejected. I'm replacing them with a series of diagonal fields with momentums of the type P0S. So for each of these three models, we have a modular invariant torus partition function. And we also have some global symmetry. So the global symmetry of ON, well, it's the group ON. Of the UN model, it's UN. And of the Potts model, it's the symmetry group SQ. And the parameters N and Q are related to the central charge. They are given by N equals -2 cos phi beta squared, and Q equals 4 cos squared phi beta squared. So I'm not deriving this equation, no, we are just accepting it. I'll give an argument for it later. However, if you notice, I mean, I have groups here whose parameters are not necessarily integer, they can even be complex. So that's not a big problem for the CFT, because what matters is not really the group itself, but it's the category of representation. And this exists also for complex parameters.
The fields listed in the table, how do they transform under the?
Yeah, that's a good question. How do these fields transform? And you have to find that if you want to understand your spectrum now. And they transform in a rather complicated way in general. So I won't talk about it really in this course, but I can give some hints. So first, the degenerate fields here are always in the identity representation. So they transform trivially. Then the other fields in general transform non-trivially. So let's focus, for example, on ON. So the simplest non-diagonal field is V1/0, and this belongs to the fundamental representation of ON, so a representation of dimension n. So if you want, you could have n indices here, distinguishing these vectors in this representation. Except that, of course, n is now not an integer, so it's a bit more subtle. I mean, but that's the idea. So you have field multiplicity. In fact, it's not the only reason why you have field multiplicity. You can have fields here which, like this, we have 0. It doesn't transform in an irreducible representation, but you can have this field with either a fully symmetric 3 tensor, or it could be a fully antisymmetric 3 tensor. So here, these are Young diagrams, which correspond to irreducible representations of ON. And it can even get worse. I mean, if you consider V5 has 0, well, you have plenty of representations here which can appear, but one of them here comes with multiplicity 2. So in this model, you have two different fields, but which transform the same for the Dirac-Molev for the conformal symmetry, and also the same for ON. But okay, I mean, that's not really our subject. I mean, here we will stay focused on the conformal side of things.
No SPN model?
Well, there's no SPN model, I think, because it would essentially be equivalent to a ON model. If you consider the category of representations of SPN for n complex, eventually you find it's the same as some ON with negative n. If you want more details about that, you can ask Paul, who is here, who worked on that recently. But I mean, indeed, there is a reason why you have only these three groups. I mean, these are the groups for which there exists the link category, which generalizes these groups to complex parameters. So we are not really looking for more CFTs because we think these are the only possibilities.
When you write this formula, it's a little magic. N and Q are functions of beta square.
Yeah, I will give an argument, but to give this relation, I will have to really tell you about the loops themselves. But that comes later, maybe next course, or the last course if I'm late. Okay, so that's all for the sketch of loop model, and also, well, for the sketch in general of all the CFTs that we will consider. Maybe you wonder why the list stops here, so let me mention the existence of some CFTs I'm not considering. So the first one is E-series minimal model. So they exist for some beta squared equals Q over P again, but now P equals 12, 18, or 30. And I'm not considering them because I don't really have a good derivation of their spectrum, so they are still a bit mysterious from this point of view. So they emerge naturally from classifying minimal models by looking at singular invariant partial functions, but in this formalism, I'm not sure how they emerge. Okay, we have a logarithmic minimal model. So again, beta squared is rational. Well, maybe it could even be negative, I'm not sure. And these are models where the primary fields belong to the extended cat table, meaning the primary fields are of the type, again, VRS, with R and S integer, but now not necessarily in the cat table. So they don't obey this, they are not in this interval. They can get outside the cat table. So I have little to say on them because the CFT is not very well understood in general, and I wouldn't even know how many such models there exist at a given central charge. And then other CFTs are free bosons. Okay, so I started with the assumption that we didn't have an extended symmetry algebra, but in fact in free bosons we have an abelian affine symmetry algebra. However, it's still possible to solve free bosons using just Virasoro and to compute, if you want, to compute correlation functions of all Virasoro primaries. So this can be done at equals 1 in particular for the compactified free boson and also for the Ashkin-Taylor model, which is the Z2 orbifold. So these models depend on R, so some radius of compactification, which is any complex number. And in fact, you can also generalize compactified free bosons, generally central charge. But if you do that, you will have to quantize the radius. Okay, but I'm not getting into that.
You just, I mean, C equal 1, you have a kind of minimal series also, which is labeled by subgroups of SU2. It's kind of equivalent, I think.
A minimal series of what? Of just of CFTs?
Yes, I think so. But it looks like the minimal, but they are not minimal.
They are kind of
special points.
Yes, special points. Yes.
You mean there are special cases of these free bosons?
Yes.
Okay, right.
All these curiosities at C equals 1 by Ginsparg.
Okay, so thank you for this precision. Yeah, yeah, indeed, I'm leaving out some interesting things. That's true. But okay, now we are more than halfway in this course about exactly solvable CFTs, and we still have to exactly solve them. So that's the business, right? That's the urgent business. So how do we solve them? Well, we solve them by analytic bootstrap. So we started by looking at the consequences of conformal symmetry. So word identities, etc., how these constrain correlation functions, including how this led to decomposition into conformal plots. And to do that, technically, we considered products of the type T, V, V. So V and V are two primary fields, and T is the energy momentum tensor. And then, using the associativity of the operator product, we could deduce the word identities, basically. And now the idea of the analytic bootstrap is to do the same thing, but instead of TVV, we'll consider our degenerate field, let's say V21, VV. So we want to find the consequences of the associativity of this operator product. And in fact, since associativity of operator product expansions is equivalent to crossing symmetry of 4-point functions, we are going to study 4-point functions involving degenerate fields. So let's consider first a generic 4-point function of some descendant. I still don't have degenerate fields at this point. So L V0 of Z, let's say, V1 of 0, V2 of infinity, V3 of 1. And then we saw that descendants are determined by primaries. So using word identities, in principle, we can write this as some polynomial depending on L. In fact, a differential polynomial in Z acting on my correlation function. So acting on V0, etc. And now, if this V0 is replaced by some degenerate field, VRS, by definition, a degenerate field has a vanishing null vector. So it obeys LRS, VRS equals 0. For LRS, some creation operator, so a combination of Virasoro generators. And therefore, if you consider, let's say, if you consider this 4-point function now with VRS, it has to vanish when you apply the differential polynomial PLRS.
Now you are again. just a function of z, not of z bar.
Well,
It's holomorphic thing.
right. I mean, this polynomial is something holomorphic. Well, the correlation function, well, this applies also to the full correlation function. Okay, so we have this differential equation, and it is called the BPZ equation for Belavin, Polyakov, Zamolan-Chekhov, and it is about 40 years old. Well, we know already the order of this differential equation because we know that this LRS is of the type L minus 1 to the R times S plus something. I mean, it corresponds to a null vector at level R times S. And therefore, the BPZ equation starts with DZ to the RS. Now, do we need to derive the BPZ equations? Well, not quite, because we know also that these two degenerate fields, V12 and V21, they generate all the other degenerate fields. So in fact, we can just focus on the cases of V12 and V21. So let's say V21. So I'm considering G of Z equals V21 of Z, and then, well, V10, V2 of infinity, V3 at 1. And I want to explicitly derive the BPZ equation for this G of Z, which will be of order 2. So how do we do that? Well, we insert the energy momentum tensor. So let's consider the following object. So Z0 of Z equals 1 over 2 pi I, an integral around Z0, dy, y minus 1, y over y minus z, and then T of y, V21 of z, etc. And Z0 here is just 0, 1, infinity of z itself. So basically I have my 4 points here, z, 0, 1, infinity, and I'm adding, well, some contour integral over y around one of these points, and on the contour we have T, the energy momentum tensor. Okay, so since we're on the sphere, we have a relation between these objects. So G infinity, basically, has to be the sum of the others. G0 plus G1 plus GZ. And then each one of these objects can be computed by just closing the contour around one of these points. And using the operator product expansion between T, the energy momentum tensor, and the primary field. What's the operator product expansion? By that time, well, you might need a reminder. So T of y, B, with some dimension delta of, let's say, 0, equals delta y minus d0 squared delta plus 1 over y minus d0 d by dz0 okay, plus something finite, but here we need to know the first finite term, which is just L minus 2, V delta of G0, and then I could go on, y minus C0 and minus 3, etc. So that was pretty much the definition of the energy momentum tensor and of primary field. Okay. So now you may fear that we've done something very stupid by setting 3 of our fields to 0, 1, and infinity. Because now in this OP, we have derivatives of the position of the fields, right? And if we have fixed the positions, we can't take a derivative anymore. But the trick is that we have used here a prefactor which is meant to eliminate these contributions, to eliminate these residues, basically. So eventually, we won't get any derivative with respect to the positions of these fields, which are 0, 1, and infinity. And what we get instead are the following. So G infinity is just delta 2 G of Z, because this contour integral only picks the first term around infinity. And similarly, G0 is just delta 1, and G1 is just delta 3 over 1 minus Z, G of Z. Okay, so the price to pay to get these simple results is that at Z itself now, if Z0 equals Z, situation becomes more complicated because I have added an extra singularity here, an extra 1 over Y minus Z. So I'll get a pretty complicated result, which is, if you do the calculation, so we still have this term, this delta, of course, but then we have a derivative term, 2Z minus 1 dZ, G of Z. But we also get Z minus 1 times, well, a contribution from this L minus 2 term. So L minus 2 V21 of Z plus etc. Sorry, not plus etc. It's not a plus, it's the other field. V. Okay, so now we use this equation here, this relation, and this will give us our VPZ equation. Because this L minus 2 now, since this is a definite field, we have L minus 2 plus beta squared, beta minus 2, L minus 1 squared, V21 equals 0. But then this L minus 1 is nothing but dz. So we get a differential equation, which I can write. Is there a minus sign? Yes, I think there's a minus sign. Thank you. So the differential equation is z minus 1 over beta squared, d squared dz squared, plus 2z minus 1 d by dz, plus delta 1 over z, plus delta 2 1, minus delta 2, plus delta 3 over 1 minus z. All this applies to g of z. My 4-point function is 0. So that's the second order VPZ equation. Okay. So next task is to solve this equation. But maybe it's time for the break. Any questions?
You are so too fast for me. You just use the OPE with V 0 or
Yeah. I mean, the basic equation is this one, which comes from the fact we are on the sphere. But then we have to compute each of these quantities, and each of these quantities is computed by using the OPE of T with the corresponding field, the field at 0, at 1, at 0, at infinity.
it did not deform your contour. I mean, I guess it must be equivalent. Contour.
Well, if you
three other points.
Right. I mean, if you want, it's as if I had started with a big contour around the 4 points and then just close the contour around each point. But the integral over the big contour has to be 0 because we are on the sphere.
C'est comme ça que je le fais d'habitude. Just because it's important that you can get rid of all the regular terms. It's not completely obvious in your derivation. You can do that, but
Right, but that's if you want that this particular. But we know from the start that it should be possible in principle. And if you accept that we can compute any descendant from the primaries as some differential polynomial, then it has to work.
So what if you only have D13? Because then in your differential operator, you're gonna get some L-3, L-2, L-1, and L-1 squared. So you won't be able to express everything in terms of L-1, which is the only one of which you know the differential action.
No, it still works for any higher order. Just I mean, even if you're L now, even if you have like L minus 17, L minus 2 to the fifth, L minus 43, V, let's say, in a correlation function, this is still some differential polynomial of the original correlation function.
It's just harder to compute.
Right. You compute it by exactly the same methods of inserting the new dimension tensor and working out word identity. So yeah, I was probably a bit fast. I think it's a very good exercise to look at this derivation and do it carefully. But I'm not sure we should do it very carefully in the course, otherwise we won't have time to do other things. Okay, no more. Okay, so let's solve this BPG equation. But from a PhD, we have an idea of what to expect. Because, I mean, this 4-point function, which obeys this equation, we know it should decompose into conformal blocks, right? But the conformal blocks are constrained by the operator product expansions, and an operator product expansion of 2-1 has only two terms. Well, two possible momentums can appear, p plus or minus beta over 2. So, for example, if you decompose this G in the channel, we get two terms corresponding to two conformal blocks. So particularly, they look like this. So we have our degenerate field here, 1, 2, 3. And here we have P1 plus or minus beta over 2. Well, so G is a sum of two terms of this type. Or it's, in the T channel, it's a sum of two terms of this type, 1, 2, 3. And now you have P3 plus or minus beta over 2. And moreover, we know, I mean, the asymptotic behavior of these conformal blocks. So for the S-channel blocks, we know, so let's rewrite this decomposition in terms of blocks and structure constants. So S-channel structure constants here, and then S-channel blocks there. And then the same for the T-channel. So let's say it's valid in any channel, X equals S, T, or U. So an S-channel block is, well, by definition of a block, it has Z to the power delta, the dimension corresponding to P plus or minus beta over 2, minus delta of P, minus delta 1, 1 plus over Z. So when Z goes to 0. And similarly, for a T-channel block, it would be for Z goes to 1, we had 1 minus Z to the delta of, well, that's P1 here, and for the T-channel block, it's P3, minus delta to 1, 1 plus order Z minus 1. So what are these numbers here? The critical, well, the characteristic exponents, in fact, associated to this block So there's a short calculation you can do, which is delta of p plus beta over 2 now, minus delta of p minus delta to 1, and the result is just beta p plus 1 minus beta squared over 2. So we expect a two-dimensional space, and the block dentals are a privileged basis of this two-dimensional space, and this basis is defined by these asymptotic relations. So the S-channel basis, if you want, made of the two solutions with this asymptotic behavior near z goes to 0, and the same for the T-channel basis. So we have to look for solutions of our differential equation with this type of asymptotic behavior. And, well, in fact, this asymptotic behavior suggests that we could redefine our G. So instead of G, we'll consider put an extra factor phi, which has the right asymptotic behavior near z equals 0 and also near z equals 1. So let's have this prefactor phi, and then if we consider phi minus 1 p of z, I mean this one, we are looking for solutions which are in fact holomorphic near z equals 0. And we are also looking for a solution which could be holomorphic near z equals 1. So it's a good idea to rewrite the equation for phi minus 1g. And this equation turns out to be the hypergeometric equation. So by this simple, by adding this simple prefactor, we change this BPZ equation into a hypergeometric equation, which I'm not going to write. I'm going to write the solution, because everything is known on the hypergeometric equation, in particular the solution. The solutions, you can match them to conformal blocks using the asymptotic behavior. So in particular, the S-channel block Fs plus is, well, z to the beta p1 plus 1 minus beta squared over 2, 1 minus z to the beta p3 plus 1 minus beta squared over 2. So here I'm copying my prefactor phi, and the rest is a hypergeometric function 2f1 with the arguments 1/2 plus beta p1 plus p2 plus p3, 1/2 plus beta p1 plus p3 minus p2, 1 plus 2 beta p1, z. So this hypergeometric function is a function of 3 parameters and 1 variable. The variable is z, and the parameters, well, they are basically the coefficients in this differential equation. But the nice thing is now we have momentum speed. We started with dimension delta, but by this transformation, we got an equation depending on the momentum. Okay, so that's just an example, but in fact, you can write similarly all these blocks, all these T and S channel blocks as hypergeometric functions.
Two functions. They can be all written with two hypergeometry, but they are the second solution of this equation.
Right. So if you look at the S channel basis, you have the second solution, which is Fs minus. But then you can adopt instead a T channel basis, and then you have two other solutions. And of course, the two bases are related by a change of basis. So, change of basis. Let me write it explicitly. Because in fact, we don't really need to know the solutions, but what we need to know is the change of basis. I mean, that's what will influence our structure constant in CFT. So, the S basis, it has to be a linear combination of the T basis, so F T epsilon 3 for a sum of epsilon 3 equals plus or minus, and then the coefficient, let me call it F epsilon 1 epsilon 3. So this straight F is called the degenerate using matrix. And we know this using matrix because we know everything about the hypergeometric function. So f epsilon 1, epsilon 3 is gamma of 1 plus 2 beta epsilon 1 p1, gamma of minus 2 beta epsilon 3 p3 over a product of two factors, gamma 1/2 plus beta epsilon 1 p1 plus minus beta p2 minus beta epsilon 3 p3. So the arguments here, I mean, in these combinations, you recognize basically the combinations which appear in the hypergeometric function, and gamma is Euler's gamma function, which is also very well known. Okay. So I think this is all we need to know about this PPZ equation and their solutions. So now we use that to do CFT.
Let me just ask you, because I forgot. This function f, it's just has pole or it has cuts?
No, f, the hypergeometric function has cuts. Yeah, if you start from this one and you try to go around the point z equals 1, then
You pick up a.
you don't come back to the same value. So yeah, it has
So just regular at 0.
right, indeed. I mean, this thing is holomorphic in near z equals 0, but with a cut.
But then why? So you multiply by a factor of z, but 1 minus z. What was the reason for the factor 1? 1 minus z delta 3. It just.
Yeah. So using these three factors, I mean, after writing these three factors, the remaining function obeys the differential equation such that there exists a holomorphic function near z equals 0, and also there exists a holomorphic solution near z equals 1. And these are properties of the hypergeometric function itself.
There is a very nice thing called a Riemann symbol, and then you understand very well what happens.
No, I don't really know about this Riemann symbol.
When you do this transformation, you get the second order equation in the Fuchsian form, and you have the exponent of each singular point. This is the Riemann.
Yeah, thank you, Raoul. So in fact, yeah, Raoul has worked on these equations, even in the case when you have W algebras, so higher order differential equations. And yeah, there is a nice story about that. You can ask him if you want. But for us, only this simple case will be. Okay, so now, I mean, we should remember that our correlation functions have to be single valued. So we are looking for a 4-point function here, which is a combination of these hypergeometric functions on the left and on the right, but this combination should be single valued. And it should also be crossing symmetric, so the decompositions in the S and T channels in particular should coincide. So what does this give us? So we start with this 2 d plus minus t ft plus minus squared. And then we can do change of basis on the left. So we can rewrite the S channel blocks here as combination of T channel blocks. And then it will give us equations for the coefficients small d. So these equations are for any epsilon bar times, we have a sum v plus minus s f plus minus epsilon f bar plus minus epsilon equals epsilon bar equals delta epsilon bar v p epsilon. Right, so I'm just injecting this change of basis here and projecting on some terms. So here I have terms a priori. This is the projection on the term ft epsilon f bar t epsilon bar. So on the right-hand side, you see you have the delta function because on the right-hand side, you only have the diagonal combination with epsilon equals epsilon bar.
You're putting back the left and right things together.
Yes. I mean, as I had it from the start, but to study the equation itself, we could forget about the right movers. It was purely holomorphic, if you want. But now I'm insisting on single validness and crossing symmetry. Okay, so does this look good? Well, at first sight, I would say it does not look good at all, because here we have 4 equations parameterized by epsilon, epsilon bar, and we have 4 unknowns, which are these d's. Look at the 2 equations with epsilon equals minus epsilon bar. So if epsilon equals minus epsilon bar, the right-hand side is 0, and therefore you get equations for just d plus minus s. So you get 2 different values of ds plus over ds minus. And these 2 results, well, they have to be the same if you want a non-trivial solution to exist. And for this to happen, you need the F matrices here to obey some constraint. And the constraint is F plus plus, F minus minus, over F plus minus, F minus plus. You get just a product plus minus cos pi beta P1 plus or minus P2 minus P3 over cos pi beta P1 plus or minus P2 plus P3. Well, we started with sin, but we get cos because we have this this 1/2 here, which shifting a sin by 1/2 makes the cos. And we want this to be the same as the same thing on the right with the P bar. But what's the relation between P and P bar, in fact? Well, now we have to remember something. We have to remember that there exists degenerate field V21 in our case. And this implies that for a non-diagonal field, the S is half integer. Right? The second index of some non-diagonal field is half integer. But the second index, I can rewrite it in terms of the momentums P and P bar. And let me make sure I don't make a mistake here. So S, if you want, is beta P bar minus P. So if you use the fact that this difference is half integer, you can show that this product is the same on the left and on the right. And therefore, our condition for this system to be degenerate is satisfied. In fact, this calculation is an alternative way of proving this type of constraint here. Well, in fact, we need not just that it's half integer, we also need that it's conserved modulo z. So in particular, if you want S1 plus S2 plus S3 is integer. Okay? So, if there is no problem, then we can really solve this linear system. Which means in particular that any one of these 4 structure constants, any one of these 4 coefficients, d plus minus s or t, it can be written in terms of just one of them. And for example, I'm just taking one relation, s minus over ds plus. And this is just, well, as you would expect, a big bunch of gamma functions. So, minus gamma 1 plus 2 beta p1 over gamma of 1 minus 2 beta p1, gamma of 1 plus 2 beta p1 bar, gamma of 1 minus 2 beta p1 bar, minus 2s2, and then product plus minus gamma of 1/2 minus beta P1 bar plus minus beta P2 bar plus minus beta P3 bar over product gamma of 1/2 plus beta P1 plus minus beta P2 plus minus beta P3. So basically this tells us how these two coefficients must be related such that this combination is single valued and crossing symmetric. In particular, this 4-point function, this degenerate 4-point function we are studying, well, we know it now, we know its d-dependence, we know it up to an overall constant prefactor. But we are not really interested in this degenerate 4-point function. We are really interested in this ratio of coefficients. Okay, so now let's deduce constraints for the structure constants of our CFT. So what are the structure constants of our CFT? Or CFT data, if you want. So there are the 2-point structure constant and the 3-point structure constant. So basically VI. This coefficient is called BI, 2-point structure constant, and BI Vj Vk is Ci Jk. So how do we constrain then? B equals 1. You want B to be equals to 1. Well, we'll do it later, but that's a choice of normalization. It's not always the best choice in a given model, if you want. So it's better to keep B generic for the moment. So the idea now is we want to express this object, this coefficient, in terms of this structure constant. But to do that, we'll need an extra auxiliary structure constant, which tells us what is the OPE between V21 and Vp. So let's call it Vi with just an index I. So this has two terms, which now I'm writing as Ci minus Vi minus plus Ci plus Vi plus. So it's just a convenient notation. By Vi minus, I mean a field with momentum minus beta over 2, Vpi minus beta over 2. And Vi plus is a field with momentum Vpi plus beta over 2. So let's look at the S-channel decomposition. So we have 2, 1 here, 1, 2, 3. So what is the coefficient of the S-channel block? So this S-channel block F plus, let's say, it comes with a coefficient Vs plus. And now the idea is that this coefficient you can just get it by looking at OPEs, in fact. So we start with our 4-point function, V21, V1, V2, V3. So we do this OPE, so we get a C1 plus, and then we get just V1 plus V2, V3. But this is just a 3-point function. So therefore, we have Ds plus equals C1 plus C1 plus 2, 3 in my compact notations, well, as well as for V minus. So here, if you want, we have 1 plus minus propagating in this channel. Right? You seem a bit skeptical. Well, I should do a poll maybe who believes this equation and who doesn't. Or maybe I should ask someone to write the next equation on the board. Okay. No, and this is just, if you want, this formula is a special case of the idea that if you do a conformal block decomposition of a 4-point function, what you get, the coefficients you get are combinations of structure constants of this type B and C. Except that they have given a special name to this particular structure constant here for these machines. Okay, so now I know the ratio of these two objects. It is given just by this big formula. So in principle, it tells me something interesting on this C structure constant, except that I have this annoying small coefficient, small c, which is not so interesting, and which I have to constrain. And to constrain this small c,